This is an astonishing space weather find. Cosmic rays are increasing at aviation latitudes. You can see the 12% increase in 3 years. 12%. And we're going to go into what scientists are saying. But according to space weather, and I'll leave links below for you for all of this, cosmic rays are increasing at aviation latitudes. New high altitude balloon measurements inside the Arctic Circle show that cosmic rays are increasing at these altitudes. Commercial flight crews and passengers traveling over Earth's poles now experience as much as 12% more radiation than they did just a few years ago. And this is what it says here. March 13, 2020. We're back from the Arctic. We have some results to share. In January 2020, the students of Earth to Sky Calculus and Space Weather traveled to Abisko, Sweden. They launched a pair of cosmic ray balloons. We'd been there before, launching 3 identical balloons March 2017. Putting all the data together, 2017 and 20, we find that radiation has increased a whopping 12% in just 3 years. The graph shows radiation dose at versus altitude feet, all the way from the ground level to the stratosphere. Radiation appears to be increasing at nearly all altitudes, even in the range of 25,000 feet to 40,000 feet where planes are flying. Polar flight crews and passengers are therefore absorbing about 12% more cosmic radiation than they did only a few years ago. Now, what is causing the increase? Solar minimum. At the moment, the sun is near the bottom of an 11-year cycle. That's at the bottom of it. During solar minimum, the sun's magnetic field weakens. It allows extra cosmic rays from deep space to penetrate our solar system. And these cosmic rays are hitting Earth's atmosphere, creating a spray of secondary cosmic rays that shower towards the ground below. Secondary cosmic rays are what we measure. Radiation centers aboard the helium balloons detect X-rays and gamma rays in the energy range of 10 keV to 20 MeV. It's similar to what you get from medical X-ray machines and airport security scanners. They've been launching radiation sensors almost weekly for 5 years, mainly from California, the home base of space weather, and cosmic rays in the stratosphere have been increasing the entire time, a sign of deepening solar minimum. The new data from Abisko, Sweden shows the increase is not limited to the stratosphere. It's also happening at aviation levels with a 3-year increase of 12%, even below 40,000 feet. And they said that they're planning to put up another balloon when they go to Sweden in August of 2020 to confirm these results. And, what do cosmic rays do now? Cosmic rays can seed clouds, trigger lightning, and penetrate commercial airplanes. Furthermore, there are studies linking cosmic rays with cardiac arrhythmias and sudden cardiac death in the general population. And their latest measurements show that cosmic rays intensifying with an increase of more than 18% since 2015. Now, according to the article of The Conversation, postdoctorate fellow high-energy astroparticle physics David Jones, an extra galactic mystery. Where do high-energy cosmic rays come from? It's been the defining question of high-energy astrophysics for the past century. Where do these cosmic rays come from? New findings from the Ice Cube Neutrino Observatory at the South Pole have brought us closer to understanding the origin of these strange rays, charged particles that originate somewhere beyond our planet and that reach Earth with varying energy levels and in different forms. In the recent announcement by Ice Cube scientists suggests the newly constructed observatory has found evidence allowing them to rule out gamma ray bursts, the most energetic explosions in the known universe, as the most likely source of the highest energy cosmic rays. This is big news. Make no mistake, he says. But to understand the significance of the finding, we first need to take a look at the history of cosmic ray research. Some 100 years ago, the pioneering Austrian physicist Victor Hess jumped in a hot air balloon and climbed to the dizzying height of 5.3 kilometers above the Earth's surface. Why? because he, as with many scientists of his day, was wondering where exactly ionizing radiation was coming from. Ionizing radiation is comprised of particles that can react with matter, radiation such as that seen in the fallout from Fukushima nuclear disaster. It's important to understand, however, that the ionizing radiation that was a mystery in the early 20th century is stopped by the Earth's atmosphere. It was the byproducts of the radiation's interaction with the atmosphere that was being observed. Hess's major achievement was to show that as altitude increases, so does the level of ionizing radiation, and so the radiation must have been coming from space. This radiation was thus given the title cosmic rays, and Hess was awarded in 1935 with the Nobel Prize in Physics for his troubles. Ever since, scientists such as myself have been wondering where these cosmic rays actually come from. And what we know, he says. While we are still in the dark about some major aspects of the origins of cosmic rays, we've made considerable progress. We know cosmic rays are made up of charged particles, primarily protons, about 89%, helium, 9%, and electrons, 1%, with heavy elements up to iron making up the other 1%. We also know cosmic rays arrive at Earth with an impressive energy range. From millions of electron volts to electron volt EV is the amount of energy gained by the charge of a single electron when it's moved across an electric potential difference of 1 volt up to more than 10 to the 21st EV, the number 1 with 21 zeros after it. Though these 10 to the 21 EV particles are the most energetic particles ever observed, subatomic particles with the energy of a vigorous tennis serve. Given the huge energy range with which cosmic rays arrive at Earth, it seems clear we need several explanations for their origin. From the Sun supplies many of the low-energy cosmic rays seen on Earth, while sources within our galaxy probably make up most of the rest. The cosmic rays are intermediate energies and probably created through the explosion of dead stars known as supernova, their remnants and other detritus from their lives. But there are still large gaps in our knowledge. There is precious little evidence about the exact sites of cosmic ray acceleration, cosmic rays being sped up to extremely high energies above what the Sun or the Milky Way can produce. At modest energies, it's very good evidence from X-ray and radio telescopes that the remnants of supernova can accelerate cosmic ray electrons. But we still have no strong evidence where cosmic ray protons, which we'll recall make up 90% of cosmic rays, are accelerated even in our most cosmic backyard. And even after a century of intense study, we still don't know the exact source of the highest energy cosmic rays, subatomic particles with energies above 10 to the 15 eV. These particles are found above what is known to be known as the knee, around our leg, the knee of the cosmic ray spectrum, and are thought to come from extragalactic sources, somewhere really way out. So how do we get about determining the source of these high-energy cosmic rays? Observationally, there are two methods, direct and indirect detection. Direct detection of cosmic rays. Due to the fact cosmic rays are made up of charged particles, they are, unlike photons, light particles, deflected by ambient magnetic fields, and as a result, the exact location of their acceleration is lost. But the relative weakness of galactic and intergalactic magnetic fields implies this does not occur for sufficiently energetic cosmic rays with energy levels above 10 to the 19th eV. Thus, it was a great breakthrough in 2007 when the Pierre Auger Observatory, a vast array of tanks and fluorescent light detectors dedicated to directly detecting cosmic rays of the highest energies, reported there was a statistically significant correlation between cosmic rays and active galactic nuclei, the center of galaxies, which contain supermassive black holes. In other words, it appeared as if high-energy cosmic rays were coming from active galactic nuclei, that is, from black holes. Unfortunately, this evidence is getting worse. While scientists at Pierre Auger Observatory were sure their data were correct and their result was statistically significant, in statistics nothing is certain. A small number of results will actually be a meaningless blip, and unfortunately for the researchers at Pierre Auger Observatory, this result was one of them. Their signal is sadly disappearing into the statistical muck of random noise. Therefore, for now, we need a non-interacting proxy for detecting cosmic rays, the neutrino. Indirect detection of cosmic rays. Neutrinos are almost massless, chargeless particles, their name means little neutral one, which are created in many particle interactions. You might remember that neutrinos were at the center of the faster-than-light kerfuffle earlier this year. The neutrinos' lack of charge and mass, however, makes them incredibly difficult to detect, and as a result, neutrino detectors have to be enormous. And as it turns out, one of the best detection mediums is the ice of Antarctica. And so, to detect neutrinos from outer space, the 1 cubic kilometer ice cube observatory was built at the South Pole. The gamma ray burst link. For the vast majority of the past century, without enormous detectors, such as IceCube, the only source of information about the acceleration of the highest energy cosmic rays was purely theoretical. Many of these theories have posited that mysterious bursts of gamma rays, that is, photons with very high energies, called gamma ray bursts, could provide a meaningful flux of particles in the highest energies. Gamma ray bursts, the most energetic events in the known universe, are observed at a rate of a few per galaxy per century. The last few milliseconds, they last from milliseconds to a minute, to minutes, and are followed by afterglows emitted at X-ray to radio wavelengths. And despite their rarity, the vast expansion of our universe makes, or according to IceCube's current research made, these events are a great potential source for highest energy cosmic rays. We know that neutrinos are produced in the same interactions that should produce the gamma rays that give gamma ray bursts their name. Hence, the theory goes, neutrinos should be observed from gamma ray bursts. And given this, it leaves particle physics in a precarious position, given that neutrinos from these gamma ray bursts are not seen by IceCube in Antarctica. The importance of no neutrinos. There are two schools of thought about the sources of cosmic rays at the highest energies. Either they're created bottom-up, accelerating from low energies, such as in gamma ray bursts, or top-down, where more energetic particles interact in some way to lose energy, creating cosmic rays. Top-down models usually posit the existence of exotic dark matter particles, although recent results suggest that even dark matter is not on as certain scientific footing as it once was. The crux of the problem, really, is that other than active galactic nuclei, that is, the black holes, and gamma ray bursts, there are no known credible sources that are abundant enough to create these high-energy cosmic rays. This fact leads us to a startling conclusion. Either the IceCube data is wrong, as with the Pierre Auger Observatory results, we might have seen a random fluctuation of the data masquerading as a statistically significant result. Our understanding of gamma ray bursts is wrong, or we have to appeal to a completely new paradigm of physics. In this new paradigm, cosmic rays at the highest energies might be created by unknown particles, possibly under the influence of novel particle physics, something we don't even know about. And this could lead to the centuries Albert Einstein or Victor Hess showing the rest of us what we've been missing this whole time. One thing's for sure, this is a very exciting time to be a particle physicist, he says. And this is on The Conversation, Creative Commons. So the conclusion is, we don't know where they're coming from. They have increased a whopping 12% in the past 3 years. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.